Now that we've finished all the different ways of solving a quadratic equation, we need to take a look at the next step, which is imaginary and complex numbers. So what I'd like to do is start off by reviewing solving one of our equations by completing the square. At this point, probably, you should be able to pause the video, do this on your own, and then rejoin me in a few minutes. Okay, so at this point, you should be pausing and saying, uh-oh, I got a negative underneath my square root. And until today, you haven't been able to handle that, and so you would just stop and say that there are no real roots. And that's true. There are no real roots. Our roots are imaginary, and that's what we're going to learn about today. So, first things first, the huge idea of the day is that when you get the square root of -1, that is equal to I. I is equal to the square root of -1. It is considered the imaginary unit. And so what we're going to do is practice taking negatives out of square roots using I. Okay? So we will be able to finish this problem after we do a little bit of review. But this is the huge idea of the day. And -1 underneath the square root comes out as I. I stands for, is equal to the square root of -1. It is our imaginary unit. So let's look at some problems just simplifying with negatives under the square roots now that we know how to handle them. So when I have something like the square root of -25, what you want to think of is, oh, this is the square root of -1 times the square root of 25. Just like when we've simplified any square root, we break it up into things that'll make life easier. Well, I just learned that the square root of -1 is I. I also know that the square root of 25 is 5, so this is I times 5. And we just like that to look prettier, so we call it 5I. So essentially what happens is this. You take the negative out, call it I, and you do what you've always done to the rest of your square root. And what happens when we do a ton of these is they start going much faster. So the square root of -16. I know that the square root of +16 is 4, and I know the square root of the -1, -1 times 16 is -16, is I. So the square root of -16 is simply 4I. Now, sometimes we can't do as much. Here, I can take out the negative I, or -1 is I. So this is I times the square root of 10. But I can't simplify the square root of 10 anymore. There's no nice perfect square number that divides into it, so you're done. And that's it. For the square root of -32, again, I'll take that negative out and call it I. And then I wonder if I can simplify 32. Well, 32 is 16 times 2. The square root of 16 is 4, so I bring that out also. So I'll end up with 4 times I, square root of 2. And finally, I put this in here to help us finish our completing the square problem. Up here, when we completed the square, we would have subtracted 2 from both sides, so there's my -2. And we got plus or minus the square root of -1. Now I know that that's just -2 plus or minus I. So again, the big idea for the day is that I is the square root of -1. Anytime you have a negative under a square root, pull it out as I. The rest of the lesson is practicing that and using it in different situations. So here we go with that. We can talk about different powers of I, or different exponents on I. So I to the 0, well, any number to the 0, 5 to the 0, 12 to the 0, x to the 0 is always 1. So I to the 0 is equal to 1. I to the first, well, any number to the first stays the same. 5 to the first is 5, 32 to the first is 32, so I to the first is I. I squared is equal to -1. And we'll use that so much that you'll just get good at it, but let me talk about why. I squared could be considered I times I. And what we learned today is that I is the square root of -1. So this is the square root of -1 squared. Squaring gets rid of square rooting, and there's your -1. Cubed is -I. Again, you're going to know these really well soon, but if you want to know why that's the case, I cubed could be written as I squared times I. Well, we just learned that I squared is -1. -1 times I is -I. I to the fourth. Well, I to the fourth is 1. I just know that. Here's why. I to the fourth could be written as I squared times I squared. Well, I squared is negative 1. Negative 1 times negative 1 is positive 1. I to the fifth is I. I just know it. Here's part of why. I to the fifth could be considered I to the fourth times I. Well, I to the fourth is 1. 1 times I is I. Okay. So I actually don't just know those. What I've done is I've noticed through the years that this is a pattern. After I get through the first 4 powers of I, they start to repeat themselves. And that's always the case. It's called modular arithmetic, when things repeat themselves. So what I've come up with is what I call this I chart. On the outside of the I chart are the first 4 exponents in my powers of I. I to the 0, 1, 2, 3. 0, 1, 2, 3. On the inside of my I chart are the answers. So I to the 0 is 1. I to the first is I squared is negative 1. I cubed is negative I. And what happens is then I can continue moving around my I chart to find other answers. So I to the 0 is 1. I to the first is I squared is negative 1. I cubed is negative I to the fourth is 1. I to the fifth is I to the sixth is negative 1. I to the seventh is negative I, and so on. You can keep just moving around the circle. And that's fine. Now what happens though is sometimes you're asked for bigger numbers. So what if I ask you to find I to the 73rd? Well, you're not going to want to count around to 73. You could, but you're likely to make mistakes. And so what you can do instead is notice that there are 4 possible exponents and 4 possible answers when you use this modular arithmetic. It's mod 4. So I take the exponent on my problem, 73, and I do some old-fashioned elementary school long division. So I'm going to divide by 4 because there are 4 possible choices. I really go back to the good old days of remainders. What I have is a remainder of 1 here. I have 1 left over that I couldn't divide 4 into anymore. From before you knew about fractions and decimals, you did division and called things leftovers remainders. This has a remainder of 1. I take that remainder of 1, I look at my I chart until I find that 1 on the outside. The outside are the exponents and the remainders. And I look inside for my answer. So I to the 73rd is I. And that's how that works. We'll practice these lots more. I'm just trying to give you a little taste of everything for homework tonight. Okay. Now, math is consistent. So one of the things you're going to notice is that we have operations that we can do with I. And I really behaves just like X. So let's just go through some of these. The square root of negative 25. Well, we learned that that's 5i. The square root of negative 49, we learned, is 7i. And again, i's behave as x's, combine like terms. 5i plus 7i is 12i. You can subtract by combining like terms. 5 minus 2 is 3. 3i minus a positive 8i is negative 5i. Now when you see a number like this, that's a whole number and an imaginary unit attached, that is what we call a complex number. And complex numbers are always an a real number, plus bi form. So that's where our title complex number comes in. We just often get complex numbers when we're doing operations with imaginary numbers. Here I have a binomial times a binomial that's double distribute. So 3 times 2 is 6. 3 times I is positive 3i. Negative 5i times 2 is negative 10i. Negative 5i times I is negative 5i squared. And now we combine like things. We have a 6. 3i minus 10i is negative 7i. And we just learned on the previous page that I squared is negative 1. And so we'll replace I squared anytime we see it with negative 1. So technically this is negative 5 times negative 1, which is positive 5. Finish combining like terms. 6 plus 5 is 11. Leave your negative 7i. Let's practice one more of those. 9 plus 2i times 9 minus 2i. Double distribute. 9 times 9 is 81. 9 times negative 2i is negative 18i. 2i times 9 is positive 18i. Positive 2i times negative 2i is negative 4i squared. Combine like terms. I have 81. Negative 18i and positive 18i cancel out. I squared is 81. Sorry, I squared is negative 1. So I have negative 4 times negative 1, which is positive 4. 81 plus 4 is 85. So it's really interesting to see that sometimes when you multiply complex numbers, you get a real number back. That's not wrong. It's meant to happen. And why did that happen? Well, if you look at 9 plus 2i and 9 minus 2i, they were exactly the same, except the signs inside were different. Those are called conjugates of each other. We use conjugates to get rid of square roots in the bottom of fractions. So a conjugate, our definition of a conjugate, is when I have the same numbers with opposite signs in the middle. So, conjugates. Write the conjugate of 7 plus 3i. Well, they have the same numbers, 7 and 3i, but the opposite sign in the middle. Opposite of subtraction is addition. So conjugates are the same numbers with opposite signs in the middle. Who cares? Well, we saw when we multiply two conjugates, we get a real number. And so to get rid of square roots or imaginary numbers in the bottom of a fraction, to make them real, we need to multiply by the conjugate. So I take 1 plus 2i and I multiply it by its conjugate. The thing is, what you do to the bottom of a fraction, you always have to do to the top. So you have two double distribute problems here. Let's go. 2 times 1 is 2. 2 times negative 4i, 2 times negative 2i is negative 4i. 3i times 1 is positive 3i. 3i times negative 2i is negative 6i squared. I'll simplify that in a minute. On the bottom, 1 times 1 is 1. 1 times negative 2i is negative 2i. Positive 2i times 1 is positive 2i. Positive 2i times negative 2i is negative 4i squared. Now you simplify each piece. Now, I squared is negative 1. So this is technically negative 6 times negative 1, or positive 6. 2 plus 6 is 8. Combine your i's. Negative 4i plus 3i is negative I, or negative 1i. On the bottom, those middle terms cancel. That's the whole point. We want them to. When we do a conjugate, those middle terms will always cancel. I squared is negative 1. So negative 4 times negative 1 is positive 4. 1 plus 4 is 5. So to simplify a fraction that has a complex number in the bottom, you multiply by its conjugate, and you get a real number back.